Welcome everybody. This is ME 760 Engineering Analysis 1. So we will continue. Hopefully today will be the last lecture for the linear algebra topic, the chapter number 10. And from next time we will start the new topic, chapter number 11, which will be vector calculus. So what I'm going to do today is just continue the iterative scheme method or iterative technique for solving the sets of linear algebraic equation. Most probably I will not go through all the techniques. Maybe I will go through technique number 1 and 2 maybe or so. And you have to print out and read the handouts for Professor Ken Schultz. The handouts are called Classical Matrix Iteration Solution Methods. So just download it, read it. If you need any question, let me know. I don't know if I will be bringing any homework problem from this topic or not, which is the iteration technique, but it is of utmost importance to all of you if you will be in, let's say, going to the graduate school, or if you are now in the graduate school and you will need to do some numerical work or numerical calculation based on matrices. This will be very helpful to all of you. So I encourage everybody to download it, print it, read it, and keep it in your folder so that you will use it in the near future if you are using this in the graduate school. So I will go through the lecture. I will go through the first iterative technique. I will not give all of them. If I have time, I will go through them. If not, you have to read the rest of the material. This is the last part of this topic, the linear algebra and matrices, and hopefully we will move on to the next topic in the next lecture. So let's start. So last time we stated that the equation that we want to solve is just AX equal to B, and we give it the star here, and then we stated that we want to solve a system with A plus A wiggle or A tilde, and this is equal to X applied over X equal to B plus A tilde X. And then when we rearrange this, we reach to the equation X equal to mx plus g, and we give this equation last time a double star, and we define the iteration to be the vector x after nth iteration will be just the matrix M multiplied by the vector x at the nth minus 1 iteration plus the matrix G. And we stated several lectures ago and also last lecture that the condition, what is the condition for the conversion of this iteration technique? So the spectral radius of what matrix? Mu for this equation. What matrix here? What's the matrix? M. So mu of M, the spectral radius of matrix M, is less than 1. And once this converge the vector x, we will obtain the correct vector x, which is a solution of what equation? AX equal B. So this equation, all what we did is just add the A wiggle or A tilde to both sides, which does not change anything or alter anything, and we reach it from here to here by inverting this one and bringing it here. And then once you get A plus A wiggle or A tilde minus 1 multiplied by A tilde is equal to M, and A plus A tilde minus 1 multiplied by B is equal to G. So we did not introduce any change to the original equation, so the solution of this equation should be the solution of this equation. And then we said that we will use, because this equation, the form of the equation now, it's easy to do iteration. So if you start with initial guess for x, the vector x, call it or name it x0, then you will get the second guess will be x1, and then you will take x1, repeat it here again, put here again, and so on. So it's now in the form that will facilitate using the iteration technique. The condition for the convergence of the iteration technique is the spectral radius of the matrix M should be less than 1. And last time we said that we will try today to prove that the spectral radius less than 1 is a condition for conversion. And this is what we will be doing here. So this is analysis of the iteration. Analysis of the iteration approach. So we will call this equation number 1. And then we will define a vector, error vector. We will define an error vector En, which is the error at the nth iteration, where En, the error at nth iteration, is just equal to the Xn, which is the vector calculated after the nth iteration minus the original vector. Of course, somebody will say, I do not know what's the original vector. Yes, of course, you do not know the original vector. This is why we'll try to reduce this to a better form to be able to use it or utilize it in numerical analysis. So the solution, X is the true solution. So X is the true solution, and it is the solution of what equation? X equal to M multiplied by what? X plus G. And Xn is what? This is the nth iteration. So this is solution after the nth iteration. So now this iteration technique, so the iteration technique will converge if e to after the nth iteration goes to 0. So it will only converge when n goes to infinity. The nth error goes to 0. So let's assume that we started 10 million iteration or 100,000 iteration or 10,000 iteration. I don't know how many, but let's say after 10,000 iteration or 1,000 iteration or 100 iteration, the En, the error after the nth iteration, the limit with n goes to infinity, this will go to 0. Of course, when you do numerical analysis, you will not of course do infinite iteration, but at least for a large number of iteration, you will say this is acceptable error. You will never look for error equal to 0. So you will say, I am satisfied with error in the order of, let's say, 10 to the power of minus 3. The difference, 10 to the power of minus 2. Let's say I am satisfied with an error 10%, error 5%, error 1%. It depends on the case or the problem that you are trying to solve and what is the sensitivity of the error, for example. So I remember I think last week when I was teaching the reactor physics equations and calculations, the students, I don't know if you know something called the infinite multiplication factor for a nuclear reactor. So the students the actual solution was something like 1.43. And some of the students, this is the actual value. Some of the students, for example, they said, oh, we just get it something like 1.37, so it's very near, it's okay, it's right. I said, no, this is not right. Because if you are a nuclear engineer, the difference between 43 and 37 is just what? 0.06? Maybe? Yes? 0.06. There is a value in nuclear engineering called beta, which is delayed neutron fraction. This beta is 0.0065. So if your core reactivity goes beyond this value, your reactor is supercritical, and you will destroy the reactor. So the change is what compared to beta? Huge. Huge compared to beta. So it depends on the problem. I'm trying to give you this example to show you that the sensitivity of your answer depends on the example that you are trying to play with. If you are designing, let's say, a highway, and the highway is kilometers, and you get something like an error of centimeters or even half a meter or something like this, it is acceptable. But if you are talking about atomic masses or nuclear masses or anything like very, very minute, and you give me something like a big difference, and you say, oh, the difference is very small, it's just 0.01 or 0.02, no, it's a big difference. So it depends. So this is why we said you will never do an infinite iteration, but you have to stop whenever, in the actual case, whenever your error will be of acceptable value according to your problem in hand. So now, this is the iteration technique, and iteration technique we will consider it converges when the limit of E after nth iteration, when n goes to infinity, will equal to 0. So now I can subtract, let's say, I will assume that I will subtract this equation, which is this one here, xn. So xn equal to m x n minus 1 plus j. Subtract from this equation the original equation, x equal to m x plus j. So this is just the exact equation, but this is the numerical analysis equation. So when we subtract those two equations from each other, we will get what? We'll get x n minus what? X is equal to m multiplied by what? xn minus 1 minus x. So what's this? Error after nth iteration equal to m multiplied by the error after nth minus 1 iteration. Yes? Then I can do the same with error after the nth minus 1 iteration, and I can make it m multiplied by the error in the nth minus 2 iteration. So this will give me m square e n minus 2. Again, I can continue this one like for m minus 3. So this will be m multiplied by m, and the error after the nth minus 2 iteration will be m error after nth minus 3 iteration, and this will be m3 n minus 3. I will go on until this will give me m to the power of n e 0. So now, instead of just defining the error to be the difference between the calculated value for the vector x minus the original value for the vector x, the true solution, I can define the error after the nth iteration to be just the matrix m raised to the power of n multiplied by the initial error. So this is better. Yes? I do not need to know now the original solution to define the error. So this is the error here. So let's try to see if we have the case for our eigenvalue problem, solve the set of linear algebraic equation. If we have for this equation for the matrix A, we have, let's say, the case where we have distinct eigenvalues for the matrix A. So we have distinct eigenvalues. So in this case, there is no degeneracy for the eigenvalues. In this case, or for the matrix M, we'll call this for the matrix M. So in this case, I can write the matrix M applied over the eigenvector U equal to lambda I multiplied by Ui. So this is just the eigenvalue problem. So Ui is the eigenvector I, and lambda I is the corresponding eigenvalue I. So this is the eigenvalue problem here. So, and if we said that all lambdas are distinct. So you do not have two lambdas or three lambdas are equal to each other. So in this case, we will notice that if the lambdas are distinct, UIs form a basis for your linear vector space. So U1, U2, U3, U4, let's say. U5 if you have 5 dimension, 5 by 5, or if you have 2 by 2 matrix, how many eigenvectors usually will have? 2. If you have distinct lambdas. If you have 3 by 3, how many? 3, and so on. If you have n by n, you have n, and so on. So those UIs will form a basis. So in this case, you can write the error vector. The error is a vector because it corresponds to what? If you have, the error is nothing more than if you have x1, x2, x3 up to xn, and this is the true value, and you have the measured value after nth iteration, let's say. So this is x1 after nth iteration, x2 after nth iteration, x3 after nth iteration, up to x. Let's make n capital here so that nobody will confuse. xn after nth iteration. So you will have a vector e1, e2 after the nth iteration, up to en after the nth iteration. So this vector, I can write it now in terms of the basis. Yes, it's a vector in the linear vector space. I can write it as a linear combination of the eigenvectors. So E0 will be just equal to what? Will be just equal to the summation from I equal to 1 to n AI UI. So AI UI. So I'm just writing the vector, the error vector at the very early beginning at iteration, the initial guess for the error E0. I will be write it as a linear combination of the vector, the basis of the linear vector space. So in this case, I knew that an is just equal to mn multiplied by e to the power e of 0, which is from here, this relation. So I can now substitute with E0 from this relation, and this will give me the summation over I equal to 1 to n AI UI. But the summation is running over what? Running over I. So I can get m to the power of n here because it's not It's not I, it's m of I or anything. So this is like a constant with respect to the I. So this will be just the summation from I equal to 1 to n ai m to the power of n ui. And what's this? What's this? What do you say? Lambda what? Lambda I2 to the power of n. Multiplied by what? ui. Okay, guys? Then, now, I can take the norm of the vector, error vector after the nth iteration, and I will take the same norm here. So this will be the norm for the summation from I equal to 1 to I ai lambda I n ui. I did not do anything except taking the norm. Now, this is lambda I to the power of n, yes? If we pick up lambda I to be lambda maximum, what will happen? What needs to be changed here? If I say I'm looking for the maximum lambda, how I will change my equation here? Summation I equal 1 to n multiplied by ai lambda I to the power of n. I replace lambda I by the maximum lambda I. So what should I put here? What should I put here? Huh? Yeah, you said something. Less than? Yeah, exactly. So I have to put less than or equal. Yes, because if lambda I is the maximum lambda, so in this case, I did not do anything, this will be equal to this. But if this lambda I is less than the maximum lambda, in this case, if I replace this by the maximum, this means that this term is no longer equal, but it is less than this right-hand side. So this is what I did. It's less than this side. So I replaced lambda I make lambda I to be equal to the maximum for all i's of lambda I, and I call it lambda maximum. Now, this part here, I can replace it by what? I can replace it by what? By the amplitude of lambda maximum to the power of n multiplied by the amplitude of what? ai ui from I equal 1 to n. What's this? Look up over there. E0. So this is equal to what? So less than or equal lambda maximum to the power of n. This value here, it's a constant vector. Yes? E0 is my initial guess. So it is a constant vector. Yes? It's not a variable or anything like this. What is the condition for conversion? Huh? No. For the error. Based on the error. Look at the... So when you take the limit for this thing, when n goes to infinity, this should go to what? 0. The right hand side, does it have any n? Yes, there is n here, but there is no n here. There is no n. It does not depend on the iteration. This is the initial guess. So this is the term, the only term that has what? N. So when this will go to 0, when n goes to infinity. Lambda maximum should be less than 1, so that, let's say, if you have 0.9, multiplied 0.9 by 0.9, this will give you 0.82, multiplied by 0.9, this will give you something like what? 0186 or something like this. So whenever you multiply more and more and more and more, this term will go to what?
0.
Will go to 0. So the condition now for limit when n goes to infinity for En equal to 0 entail that lambda maximum to the power of n, or sorry, lambda maximum is less than what? Less than 1. And this is the derivation that we stated last time. So in order to converge the nth iteration error, the limit for n goes to 0, the error should go to 0, and this entails that your spectral radius should be less than 1, so that you will converge. Guys, did you understand? Okay. So now, let's take a note and now look for if mu n, which is just, mu is the spectral radius, which is the maximum of lambda, which is lambda maximum, amplitude of lambda maximum to the power of n. If mu n is very near to 1, what will happen? Your convergence will be slower or faster? Slower, because you are very, very near to 1. If you are 1 and above, you don't converge. So if your lambda maximum is very small and near to 0, so you will converge very, very quickly, very fast. So we want to measure a rate of conversion, and we will define conversion rate R. And this conversion rate, we'll define it as R equal to negative d by dn. Of course, I have to differentiate with respect to the number of iteration of len error after the nth iteration divided by the error, the initial guess for the error. And this will be equal to what? What's the differentiation of the logarithm?
The logarithm of the numerator minus logarithm of the denominator.
No, the differentiation
Oh.
is 1 over whatever inside the logarithm multiplied by the differentiation of what's inside the logarithm. But as you said, let's just take d by dn and decompose this. So when you decompose this, this will give you len En after the nth iteration minus len E0, which is the initial guess. But what's d by dn for this term? No, it's len. This is len, not len. Logarithm of something does not have any n on it. 0. So it's a constant. It does not depend on n. So when you differentiate this part, this will give you 0, and this will give you what? 1 over minus 1 over En. Yes? Multiplied by d by dn Yes, guys? So this is R. Or I can define it also in another way as I can define it as R will be negative d by dn for len mu to the power of n. And this will give me what? Negative n. This will be negative d by dn, and this will be n ln mu. And finally, this will be, this is constant, so this will be d by dn for n multiplied by a constant is the same constant multiplied by 1, so this will give you negative ln mu. So now the rate of convergence is just negative ln of the spectral radius. So if we try now to get ln, the error after nth iteration, and plot this with nth iteration, this will give me something like this. So the slope, this slope is just equal to what? Ln mu. This is the slope, ln mu. So if mu, and it is negative slope, so you have a negative slope here. So if mu is large, what will happen? The slope will do what? Slope will increase. So you expect for large n, the slope will do what? Until you get what? 1. This is the slope of, yes? Yes, zero slope. But if mu is smaller, you expect something like this. So when the spectral radius is smaller, you expect the limit, the ln of the n, you expect n to be what? Very small. What does it mean? You expect convergence after just very small number of iteration. When the spectral radius increases, you expect what? You expect to converge after, let's say, after a larger n, and the rate of conversion will be slower. Did you understand? Now, let's take an example now and try to look for the linear Jacobi method for solving the linear system of algebraic equation. And this method is not again in the book. It is in the handout written by Professor Ken Schultz. It's out online. Here is the handout, so you have to download them and read them. So let's assume that we will have a two-dimensional heat conduction problem. So we will build up a mesh like this, and it will be two-dimensional mesh. And at each node, and a node is defined as the intersection points here. So let's assume that this node is called P, and I will define the nearest four node points. Sorry, nearest node points will be just I will call this east, and I will call this west, and I will call this one north, and I call this node as south, and I will call this node P is at I and J. So this is J here, and this is I here. So this is just a two-dimensional mesh, and you have the central point P, and you have the four nearest to the central points will be just east, west, north, south, and you can start the naming, for example, to be, let's say, 1, 2, 3, 4, blah, 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 up to I, and then this is I plus 1, I plus 2, up to here. Then once you come, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on. So you are moving left to right, left to right, left to right, left to right, and so on. Or you can do the naming 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. So you can do it in a row format, or you can do it in a column format for your problem, for example. So we will be using the finite difference scheme in order to be able to solve the two-dimension heat conduction equation, for example. Then all of us knows that the heat conduction equation is just Q double prime is just equal to negative K, let's say, dt by dx, or something like this. But this is just in one dimension, but let's say if we try to solve the two-dimension heat equation, for example, this is just one dimension heat equation. But actually, you can call it like W square T plus something. So let's assume that we are solving, let's say, the heat diffusion equation, and you want to integrate over the control volume centered around point P. So you want to integrate over this control volume here. So in order to do this integration, and usually you will have A P multiplied by the temperature. So each one of those nodes, you will have a temperature defined at each one of those nodes. So Xij will be just the temperature at the node Ij. So this is A point P, the coefficient here. The coefficient here will be the heat conductivity, for example, multiplied by a constant or something like this. So AP Xij plus A east multiplied by Xi plus 1 and J plus A west multiplied by Xi minus 1 and J and A north multiplied by Xi and J plus 1 plus A south multiplied by Xi and J minus 1, and all of this equal to some constant here, Bij. So whenever you will compose the matrix, the coefficient matrix, of course, this system will be written as Ax equal to B. And when you compose your matrix, you will notice that those are x1, x2, up to xn. So it depends on how many nodes, for example, equal to some B here, B1, B2, Bn. When you compose this, you will notice that you will obtain five diagonal matrix like this, and everything outside is 0. Everything is outside is 0. Let's look for the node at Ij. So here, this point, this is the coefficient matrix. So it will have here at this point, which is the central point, point P, it will have A, P. And the one next to it, from both sides, will be just A to the east and A to the west. And the ones farther away will be A south and A north. So in between here you will find, let's say, maybe zeros also. So this is called 5 diagonal matrix. And this is just coming from the node Ij. Yes? If you take any nodes, let's say, if you take any nodes here, this nodes, you'll have again 5 nearest points, and it will be somewhere, let's say, somewhere down here or something like this. So why we have 5 diagonal and everything is 0? Because there is no coupling between this point and this point. So this point only will see the coupling between this. So the coupling to this point will come from the 4 nearest point, and there is no coupling from far away points. So in this case, the coefficient will be just 0 multiplied by, because if you look at this point, for example, this is, let's say, this is 2 and 2, I equal 2 and j equal 2. There is no coupling between 2 and 2 and ij. It's very far away. So the contribution and the coefficient matrix will be just 0. So you multiply 0 by this contribution to this point here. This is why you will have 5 diagonal matrix like this. So the idea here is to solve again. The idea is to solve the equation x equal to m multiplied by x plus g. So we remember that we need to get a wiggle, and now I will tell you how to choose a wiggle. So a is just our diagonal 5 diagonal matrix. I can write it as a diagonal matrix minus lower diagonal minus upper diagonal. So all what you will do is you will take this diagonal here and make it the matrix B, and everything will be 0. So you will have matrix B, just the diagonal with AP, and everything is 0. And you subtract from it the lower diagonal, which is just the A south, A west, and everything else will be 0. So you will have A south, you will have A west, and everything will be 0. And this is the upper diagonal, and the upper diagonal will be just the other two, which will be A east and A north, and everything is 0. Then when you do this, you can now take a wiggle or a tilde to be L plus U. So if you take a tilde to be L plus U, what's the matrix M is defined as what? A plus a wiggle to the power of minus 1 multiplied by A. And this is equal to what? Matrix A is B minus L minus U. And A tilde is L plus U. So I will end up with what? B minus. Yes, guys? Multiplied by what? By A. And what's the matrix G? Matrix G is A plus A tilde minus 1 multiplied by what? By B. Matrix B. So this would be what? B minus 1 multiplied by the matrix B. So now I converted my matrix M and matrix G to very easy matrix to calculate. The original matrix A, I have it here. I will not do anything with the original matrix A. Then I will multiply it by what? By a pure diagonal matrix, but it is the inverse of the pure diagonal matrix, which is very easy to do. Last time I showed you that if you have a diagonal matrix, how you will get the inverse of the diagonal matrix? Invert each one of the row elements. So instead of D11, D22, D33, D44, D45, DNN, it will be 1 over D11, 1 over D22, 1 over D33, 1 over DNN. So this is very easy to calculate. And again, this is the coefficient matrix, the constant matrix. You will multiply it by the same inverse, which is very easy to do. So this is just a description, and the technique itself is described in the handout by Professor Ken Schultz. So I will stop here today, and I highly encourage everybody to read it. So just download it, read it, and if you do not understand anything or you have any questions, let me know so that I will be able to help you. Next time I will start chapter number 11, which will be the vector calculus. So see you all next time. Thank you so much.